at the Emerging Technologies Research Center, De Montfort University in 2003, and Professor of Microelectronics at the University of Sheffield in 2007. She has been a technical and executive committee member of IEEE International Electron Devices Meeting and a technical committee member of IEEE International Reliability Physics Symposium for 10 years. Now she's a technical committee member of the European Microwave Conference, ESREF, ISPS, etc. So she has published over 100 journal papers and 150 conferences. With that, please kindly mute your microphone and let's all welcome Professor Merlyne to deliver her talk. Okay, the platform is yours, Professor.
Thank you, Suhana. Let me just put this in order, and it's my real pleasure to have to be given this opportunity to give a talk to such an active chapter, and I'm really delighted to see so many activities and events being organized by the EDS Society. Today I'm going to talk about a topic which is quite close to my heart and lies at the basis of all microelectronics, and it's about CMOS to neuromorphic computing. Now, virtually every electronic device that we have has a transistor inside it. In the old days, the computers were quite distinct from communication devices. But ever since the evolution of the mobile phone in parallel with laptops, you can see that last year the Lenovo 2020 not only has a traditional CPU, but it's also got chips for AI as well as antennas to be able to communicate to other devices. And we can well imagine that in the future, computers are going to be having wheels and are going to be able to take us from place to place. Now, what are transistors made of? They're actually made of sand. And because sand is so abundant on Earth, it's one of the reasons why microelectronics has become so pervasive worldwide. Now, sand is silicon dioxide. And from silicon dioxide, we get silicon, which is the most basic material that has supplied the microelectronics industry. Now, silicon has an atomic number of 14, and we can ignore the 10 electrons which are present in closed shells. We are just left with the 4 outermost electrons which dictate the properties of the material. And by sharing these electrons with 4 neighboring atoms in a tetrahedral configuration, we are able to see that each silicon then has 8 electrons in its outermost orbit. Now, this takes us to the situation of what happens when we have a single atom versus a number of atoms. When we put these atoms together in a lattice, these electrons in the outermost orbit begin to interact with each other, and they have discrete energy levels that these electrons can have. That means the electron cannot have an arbitrary energy. It is a fixed value, and the highest occupied energy level or energy band is called the valence band. Whenever we have a crystal, we plot energy versus the momentum because of Heisenberg's uncertainty principle. Now, this occupied valence band at 0 degree Kelvin is separated from the empty energy level, lowest energy level called the conduction band, which is separated by a small band gap. And that is what makes the material a semiconductor. If there is no gap, it becomes a metal, and if it has a large gap, it is an insulator. That means it is not conducting. Now, the Fermi level is a hypothetical energy level within this band gap that tells us how many electrons are there in the material so we can control its conductivity. So take for example, if we replace one of these atoms with boron, which has only 3 electrons in its outermost orbit, that means it has 1 electron less. And that introduces an energy level within the band gap, which is quite close to the valence band. And that allows at room temperature electrons from here to jump into these energy levels, leaving behind holes for conduction. And that's known as p-type doping. It makes the silicon p-doped. On the other hand, if we replace the silicon atom with phosphorus, this has 1 extra electron here. And it introduces a donor level, which is quite close to the conduction band. At room temperature, these electrons can hop from atom to atom. They are freely available for conduction. And this is what makes this material n-type doped. So if we take 2 of these n-doped regions, which we call source and drain, and they are separated by a lightly doped p-type region, which we call as the channel. On top of the channel is the third terminal called the gate. And this, under the gate, is an insulator, insulating oxide. So this metal oxide semiconductor field effect transistor is a 3-terminal device or a switch, which is the basis of CMOS. Let's see how it works. So when you have 0 voltage on the source, the gate and the drain, the electrons here have a barrier because they face a potential barrier, so they cannot easily go from the source into this channel. When we apply a positive voltage here, we know electrons here are negatively charged. So this has the effect of reducing the number of electrons here. So the Fermi level goes down because of this positive voltage, and it creates a slope in the energy level here. But still, this electron cannot surmount this barrier. What happens is when you apply a positive gate voltage, that changes this source to channel barrier, and it creates a channel. It inverts the surface here and creates a surface channel of electrons. And this then allows the electrons to flow from the source to the drain because this is sloping downwards. And this transistor then becomes a switch, exactly like a light switch. You can turn it on or off by the application of this voltage. Now, to understand this better, let's look at the energy band diagram under this channel region here in this part as a cross section. Here we've got a metal. It has no band gap, but it is defined by something called the work function. And that's the energy that you need to give to the metal to take an electron from the metal into the vacuum level. And here we've got the p-type silicon. It has a small band gap, 1.12 electron volts. The Fermi level is in the lower half of the band gap, which means that it is p-type silicon. And in between these two is the insulator. Traditionally, it was silicon dioxide, and it has a large band gap, which means that electrons cannot go readily through the from the semiconductor into the gate or vice versa. What we notice here is that the Fermi level here is different from the Fermi level here. And it is much like a reservoir of water, except that there is no direct pipe that will connect these two sides. Let's look at this situation where we apply a negative gate voltage on the metal. So when we apply negative, this is electrons, that has the effect of increasing the number of electrons here. So it pushes the Fermi level up. But here looks what happens. these energy bands react to it and they try to reach the Fermi level, tries to reach this level on the other side, and it starts to accumulate holes near the surface. So this condition is called accumulation. If, on the other hand, we apply a small positive gate voltage, that has the effect of reducing the Fermi level on this side, and it bends the bands downwards. It depletes the holes on the surface because this is p-type, and that condition is called depletion. Now, if this gate voltage is much higher, very much greater than a certain level, it pushes it really down, and then the intrinsic level crosses the Fermi level here on this surface. And what this does is then it accumulates electrons at the surface and creates this channel that allows the electrons to flow from the source to the drain, as I've just explained before. Now, if we take two of these transistors, one is a p-type transistor, and this is an n-type transistor and this is a p-type transistor, so they are complementary, and we connect them together. That is, for the p channel we connect the source to VDD, and n channel we connect the source to ground. We connect the two drains together and the two gates together, and if we apply a pulse like this at the input, what we get at the output is an exact opposite, and this is known as a CMOS inverter. And because of this CMOS inverter, it has introduced this huge revolution over the last 50 years, which has allowed us to enjoy all of these microelectronic devices. The main reason is that only one of these transistors is on at any one time, and that means the power consumption is very low. Now let's look at the transistor characteristics. As a switch, what does the current from the drain to the source, from the source to the drain look like versus the applied gate voltage? If you look at it on a linear scale, that's this figure in red, below a certain voltage, that is before the inversion layer is formed, there's very little current that flows through the device. But beyond this threshold voltage, you can see that the current increases linearly, and it's proportional to the charge, because charge is Q equal to C times V, and we subtract the threshold voltage from the gate voltage because that amount of voltage is required to create this inversion channel, and it's proportional to the mobility of these carriers, and it's proportional to the electric field which drives the carriers downwards in the case of this electron. So that is the drain voltage divided by the length. Now, although we think there's no current flowing when the transistor is off, if you plot it on a log scale, you can see that it is a straight line. And that means there is a current that is exponentially dependent upon the applied bias. And you can also note this factor, which is Q by KT, and is called the Boltzmann's factor. Now, why do we get this subthreshold current? So it is these electrons in the tail end of this Boltzmann's distribution which have got sufficient energy from the thermal vibrations called phonons in order to cross this source to channel barrier. Now, how do we judge the devices? What do we want out of the transistor? We want the transistor to be fast as fast as possible. We wanted to switch fast, and to understand how that works, we know that the current is rate of flow of charge. Therefore, the transit time is given by the charge divided by current, and charge is nothing but C times V, where C is the load capacitance, or the number of transistors that are driven by a given inverter. It's called fan out. Now this is obviously dependent on the square of the channel distance. That means longer the distance, the longer it takes for the electrons to transit from the source to the drain. So to make the device faster, we need to scale this channel length, but it's not enough just to reduce the channel length. We need to reduce also the junction depth and the thickness of the insulator. And that has brought about a whole load of challenges. Now, the second criterion is that we want power consumption to be less because we want our devices to be cool. And that depends on two factors. One is the dynamic power consumption when your device is switching from the on to the off state. And here it is given simply by the energy, which is half CV squared divided by the time. And time is the opposite of the frequency. And the second component to the power consumption is the static power consumption when the device is off, and that depends on the leakage current times the drain voltage. So it's given by VI. And you can see that in both of these cases, in order to reduce power consumption, you need to reduce the drain supply and you need to reduce the leakage current. In fact, decades ago, you can see that also the static power consumption has overtaken the dynamic power consumption of the transistor way back in 2006. So what has industry been doing all along? They want to make devices faster and cooler. So in 2003, they introduced strain in the channel to increase the mobility of the carriers, and that was done by introducing silicon germanium stressors. At the 65 nanometer technology node, there were two companies, and we worked with one of them to introduce indium into the channel. And indium gives what is known as a retrograde channel profile. That means the peak of the profile is quite away from the substrate, and that reduces the dependence of the threshold voltage on the drain bias. It's an effect which is known as DIBBLE, or drain-induced barrier lowering. And then subsequent to this introduction, which by the way, this technology is still in production today in the technology nodes today, industry at the 45 nanometer node introduced the high K metal gate. That was to reduce the leakage current from the source into the gate because the silicon dioxide insulator had become too thin. And this introduced a lot of problems, including scattering, charge traps, and so on. And we worked with US industry at the time to understand and resolve some of these issues. At the 32 nanometer node in 2009, self-aligned via patterning was introduced. And in 2011, Intel was the first company to move away from the planar geometry and introduce the FinFET. Now, what the FinFET does is that it allows the gate to wrap around the channel, and this increases the electrostatic control and also boosts the current density. And since that time in 2011, all that has happened is that the fins have become taller and thinner in order to boost the performance. Now, this then represents a snapshot of the history of the transistors. We look at the number of millions of transistors versus time, and you can see that right from the beginning in the 70s, when we had the 10,000 nanometer node, we just had about 1,000 transistors on a chip. But today, the EPIC ROM at the 7 nanometer node in 2019 held 32 billion transistors on a single chip. And this has happened because every 2 years the feature size scales by 0.7 times, and that doubles the number of transistor count on a single chip. But you can see that in 2021, we have gone down to the 3 nanometer node from TSMC and Apple. And the question is, what is coming next? Because it's getting more and more challenging to continue to drive and give enhanced performance for CMOS. Now, the main thing is to look at how we can reduce the supply voltage. And to do that, we go back to this subthreshold characteristics of the transistor. And we know that we had to plot it in a log scale versus VGS or VDD. And what we see here is that there is a slope here which is 60 millivolts per decade. What that means is that reducing this gate voltage by 60 millivolts increases the current 10 times, and that reduces the on-off ratio. And that is not good for the device because it means it cannot drive that many layers of CMOS, or the fan out goes down. What we really want is a transistor that will switch abruptly, and it will beat this Boltzmann's limit, 60 millivolts per decade, which is known as the Boltzmann's limit. What are the origins of this subthreshold leakage? Now, in the subthreshold regime, that is below the threshold voltage or the full inversion layer is formed, the drain current is exponentially dependent on the surface potential of this channel and divided by KT because of this thermal energy of the electrons. And the subthreshold slope is simply dVg by d log IDS. It's the slope of this line. And so by multiplying and dividing by d psi s, we can get two factors. The first is called m, the body factor, and the second is called n, the transport factor. And we want to know how we can control this so that we can have a handle on this subthreshold slope. The first option is the one that manipulates the transport factor, and it's called as a TunnelFET. And that device is shown here. And in a TunnelFET, what is done is that you swap one of these source or drain to opposite polarity of the doping. And as a result of this, instead of the tail end going from the source to the drain, it's the bulk of this Boltzmann's distribution which tunnels through the channel region. The main problem with the TunnelFET is that it has a lower current than a MOSFET, and it is not scalable, and it is affected severely by defects. So it's very, very challenging to use this to get that enhanced performance in terms of switching speed and the drive current. The second option is the body factor. And let me try and explain this. We go back to the symbol of a MOSFET. This is the source and drain separated by the gate. Now we know that when we apply a positive voltage on the gate, that voltage gets dropped across the oxide, and the remainder gets dropped across the surface of the semiconductor here in order to create this inversion channel here. So VGS is Vox plus psi s. Now we are ignoring the work function of the metal for simplicity. And if we differentiate it here, the body factor is then dVGS by d psi s. It's the rate at which the gate changes the surface potential. It indicates the coupling between the gate and the semiconductor. That means if all of the VGS was dropped only on the semiconductor here and there was nothing dropped across the oxide, then M would be equal to 1. So there are two cases here. Here the numerator is greater than the denominator, dvox is greater than 0, m greater than 1. But to get m less than 1, the numerator must be less than the denominator and dvox must be less than 0. That means the dvox must be opposite to the applied electric field on the gate. And that causes an internal amplification inside the insulator itself. Let me try and explain it visually, where I've sort of represented like a beaker containing water, because I like to explain with reference to water. So we apply a certain voltage on the gate, which is represented by this red lines, and call it dVGS. If n was 1, then all of this voltage would be dropped across the semiconductor alone, and that would give us d psi s equal to dVGS, m equal to 1. But for m less than 1, what we are seeing here is this. We are applying a small voltage on the gate and getting a huge change of potential on the semiconductor. That means we are amplifying this voltage inside the insulator even before it reaches the surface of the semiconductor. And how is that possible? That happens by a phenomenon called as negative capacitance. Now, we know that in a conventional capacitor, it consists of two parallel plates. If you apply a positive voltage on one plate, it attracts charge of the opposite type, polarity on the opposite plate, and gives it a capacitance. Now, the energy stored in a capacitor is U versus the charge is parabolic in shape. The energy is given by half CV squared. And if you differentiate this curve, you can then plot the Q versus the electric field. That means the higher the voltage you apply across this capacitor, more and more charge gets attracted linearly inside the on these plates, and that the slope of this line Q versus the electric field is called the capacitance. It depends upon the dielectric constant of this material in here. Now, in a negative capacitance, the U versus the Q is not a parabola. It is W-shaped here. And if you differentiate this curve, you see the capacitance here, or the inverse of the capacitance. The inverse of the capacitance is a parabola here. And you can see that in this particular region of this W-shaped curve, the capacitance is less than 0. That means it is negative. For this W-shaped energy profile, if you plot the Q versus the epsilon, it's actually S-shaped curve. That means as you increase the electric field across the plates of this capacitor, that starts to increase the charge until it reaches a certain point. Then when you reduce the electric field, instead of charge reducing, it continues to increase until it reaches this point, and then again it starts to show an increasing behavior. But in actual practice, what happens here is that as you increase the electric field, the transistor will suddenly swap over to this point, and then you get a sort of a hysteresis. And you can see that these two states correspond to these two regions of the U versus the Q curve. So this phenomenon is known as negative capacitance. And this is just a simple example to explain what it means. Suppose we apply 5 volts on the gate and say we keep increasing this gate voltage. At this point, 3 volts is dropped across the oxide and 2 volts are dropped across the semiconductor. When you increase this gate voltage, say to little bit to 5.1, Instead of continuing to rise, the transistor swaps over to this point, and you can see that now the oxide has only 2.1 volts across it, and much more of this voltage is dropped across the semiconductor. That means the channel charge has gone up, but dVOx has gone down, and this gives us what is known as negative capacitance. Now, how do you get this negative capacitance? You use an insulator which is a ferroelectric material. It has two dipoles inside it, and based on the orientation of these two dipoles, it gives you these two states here, which ends up in you getting a hysteresis in the curve. And this is known as a ferroelectric FET, but it is more like a memory device. What we want in a CMOS is to get rid of this hysteresis. We want a curve which has no gap between them as you increase the gate voltage or you reduce it. And to do that, this was proposed by Salahuddin and Datta in 2008. You need to stabilize this transistor in this negative capacitance region by introducing a small or thin oxide capacitor in series with the ferroelectric. But that seems a little bit harder than in practice, because there was a big review in 2019, and you can see that the smaller the subthreshold slope, the bigger is the hysteresis. As you start reducing the hysteresis, the subthreshold slope starts to increase. And this has been the biggest problem which has been challenging industry for the last couple of years. So there are two schools of thought about this. The first is on the left, where by and large, for example, Salahuddin Datta, Suman Datta, and that group of people use what is known as this LK equation to describe this ferroelectric. Now, this LK equation assumes the ferroelectric is a single domain crystal for which the electric field is given by this RC circuit. But here the capacitance is given by a polynomial which represents this S-shaped curve. And this R factor here
What's the secret of a happy home? Everybody gets what they want. Me included. With Unify, my entire family.
So the resistor, this resistor is dependent upon the resistivity of the material, and this alpha less than 0 defines this S-shaped curve. That means it is a negative capacitance, which is in this LK model. Now, this type of a circuit, if it is stabilized in this region under quasi-static conditions, will give you steep switching in both the forward and the reverse sweeps. But in the early 90s, we had another model of a ferroelectric called the Miller model. And that assumes that inside the ferroelectric are multiple domains, and these take a certain amount of time to switch. They don't need any negative capacitance effect. And because of the time it takes to switch these domains or these dipoles, you get what is known as transient negative capacitance. So this circuit is exactly the same as this, except that this capacitance is always positive. It does not need this capacitor to have this negative region. And both of these models employ variable capacitances. And the question that we have been asking is this really essential? Is this the only situation where you can get steep switching? And the answer is no, because we've just reported that even if you keep a constant capacitor in your circuit, you can still get a body factor which depends upon the scan rate, because basically the reality is that you can have a material which is a combination of these two situations. It's not really that a ferroelectric has no resistivity, or it does not, there is no scan rate associated with these measurements at all. So based on your scan rate, you can see that in the backward sweep, you can get a sub 60 millivolts per decade in your transistor, even if you don't have any ferroelectric. But in the forward sweep, typically the subthreshold slope gets degraded. And the condition for getting steep subthreshold slope less than 60 millivolts per decade in the forward sweep typically occurs when the device is in the off state. So you can't really get rid of these two phenomena and consider them as separate. That's the first conclusion. And you don't even need a ferroelectric to give the steep switching, because we have shown a solid electrolyte FET where we have a very thick insulator. This is not a ferroelectric material, but inside this material, we've got oxygen ions and vacancies. And by applying an electric field, we can separate them out at the two interfaces. And this separation creates an electric field which is opposite to the direction of the electric field, applied electric field, and creates a steep switching that we have experimentally demonstrated. So we've shown all, this is not an optimized device, so the scan rate is very low, but that does not mean that there is any limitation. We have published a lot of work. Now, each of the neurons can do all of the tasks. It can store memory, it can compute, and it can communicate. And it works on the principle of spike timing dependent plasticity. Now, what does this mean? Now, if the presynaptic spike comes before the postsynaptic spike, then the timing difference between these two spikes is positive. That means this spike, this neuron spiked because this neuron sent it a message just beforehand. And so this strengthens this connection between them. Okay, it's potentiated. That means there's a strong connection. On the other hand, if this one spikes before this one, that means it spiked because of some other neuron, not this one. So the connection between these is depressed. And it's the timing difference between when these neurons receive spikes which allows the brain to learn. And so the emphasis now is on a memory device. A memory device is simply the future of memory device is a memristor. It's a two-terminal device which is a resistor which has the ability to remember. And it just has two electrodes which are separated by an oxide, for example, and it has two states. So as you swing the voltage, it has a high resistance state with low current and a low resistance state with high current. And there are 5 different types of memory devices. I won't go through them because we are running short of time, but these basically are able to change the conductance levels so that you can store a 0 or a 1. So how does the brain work? We connect all of these memristors in a dense network, which is called as an artificial neural network. And let's consider a simple example of image processing, which is what our brain is very good at. We take this image and we divide it into small pixels, and let's say the black is a 1 and the white is a 0, and we convert that into the voltage. This is 1 0 1 0 or whatever. We scan this and we feed it to these memristors. This application of the voltage controls the current because V equals IR. Okay, and this all of the currents from these memristors are then summed up, and this gives us this total current, which by Kirchhoff's laws and Ohm's law means that we are getting the addition and multiplication operations automatically when you connect them in an artificial neural network. Now we've got all of these current levels, but we don't know what it means. We then need to feed it into a neuron. And what a neuron does is it does thresholding. For example, it decides that if your current is, say, less than 0.5, it's a 0. Whereas if it is more than 0.5, it's a 1. So even if there was a color image here, a simple perceptron which does a binary, it binarizes this image, it makes it into a black and white image by controlling or making this decision. And from there, you then get an inference based on which during the learning process, you can feed back the voltages and make corrections to adjust the conductances of these memristors. Now, the simplest neuron, of course, was on or off, but you can have more sophisticated ones to allow more information. You just don't, all the world is not black and white. You want more complicated information. So you've got a large number of possibilities for neurons. In order to have this feedback path possible, these functions must be continuously differentiable, and that makes this a process of supervised learning. But then there are other more energy efficient neural networks where instead of just taking 1 or 0 every time, you can consider the probability of switching versus the voltage. And you can accumulate all these until it reaches a certain threshold, and then it emits a spike. And these are known as spiking neural networks because they are more close to the leaky integrate and fire neurons which are there in the human brain. Basically, what it does is that the reason why this artificial intelligence has taken off so quickly is because you can very easily integrate the memristor on top of the drain, especially a 2-terminal memristor on top of a drain of the CMOS, and you can very easily build these artificial neural networks, and then you can use these as compute in memory. That means you can do addition, logic, everything inside the memory itself. You want to break this Von-Neumann bottleneck where the memory is separate from the CPU. And so we've shown the same thing can be done with our SE-FET compared to, for example, a ferroelectric FET. We have shown a single transistor to do all 16 logic operations experimentally. And in fact, we can also train our device to do OR and AND operations by connecting it in an array, a crossbar array, in an artificial neural network. We have shown the device to show spike timing dependent plasticity as well, and that we can control the postsynaptic current even with the frequency. So this is very similar to some things which are happening in the brain. And more than that, our device is an active memristor because it's got a redox mechanism that happens inside the gate, which means that it has the potential to actually be used even as a neuron, not just as a conductance, as a synapse. And looking well into the future, this is the state of the art when comparing energy efficiency versus density with CMOS neurons. But looking into the future, I think there can well be a time where you can have artificial neural networks to exceed the capability even of the human brain. So just to conclude, I think there's plenty to do despite nearing the end of Moore's law. It's energy efficiency that will drive the future of human society. And we need young engineers such as yourselves to drive responsible innovation. Just towards the end, I'd like to say that, I have an initiative with the EDS Society where there are funds available to students, undergraduate, newly graduate students, PhD students, to spend time in companies in any of these areas. And if you want to do that, just send me a copy of your CV and a company that is willing to host you over the summer, and I'll be very happy to consider your applications. I'd like to thank you for your attention and your patience, and acknowledge many of my students without which this wouldn't have happened. Shaya Song, Aditya Poluri, Jingui Ju, Ashwani Kumar, and Premlal Pillai. Thank you. Thank you. I hope that was on time.
Yes, sure, Prof. Thank you so much, Prof. Merlyne De Souza, for very impressive lecture. I hope I'm not muted. Hold on. Can you hear me?
Yes.
Okay. I personally think that you have brought semiconductor electronics to a different paradigm, Prof. And you approached the theories, the current technologies, and brought the neuromorphic computing with not a peek into the future, but actually a vast peek into the future. Now, I'd like to open if there are any concerns or questions from the audience, if there are any. Okay, there's none in the
Souza. Prof. Souza.
Yes.
Yeah. I live if you can go to slide number 45.
Yes.
Okay, you were mentioning just now that the CMOS neuron can exceed the human brain. From your experience and knowledge, when can we achieve to that particular target?
Okay, so these are CMOS neurons, and we really need to move away from CMOS neurons. Actually, we need new mechanisms and new types of phenomena that will beat CMOS. CMOS neurons are very expensive because you need a lot of gates in order to give that thresholding effect, you know, that it accumulates a lot of voltage on the membrane and then spikes. So you want that phenomenon to come out naturally, and people are discovering, such as this SE-FET, for example, where even with gate voltage, you're having a current, you see here. So you can get this type of mechanisms which can beat CMOS neurons. Yes, so this, we don't know when this might happen, but you know, this is what I think people are trying to move towards.
Thank you, Prof.
You're welcome.
Prof.
Yes.
I would like to ask. Now the the channel length getting smaller, and smaller.
Yes.
And the latest one, as you mentioned, that in 2019 is already 7 nano.
Yes.
What do you think about the graphite material, which is now being used as an interconnect?
Yes, it is being graphene actually. So there are
graphene. Yes,
that is true. So what you can do is that Intel has just made an announcement in July last month, about a week ago, on their 1 nanometer technology node, and that shows stacks of these two-dimensional materials in a FinFET architecture to boost the performance even more. So today's technology is not 7 nanometers. Today's technology is 3 nanometers from TSMC. And by 2024, Intel have declared that they are going to bring out this graphene or two-dimensional layered ribbon structures in a FinFET to give the 1 nanometer node.
So we are using the graphene for the latest CMOS production, is it?
Not today's, I think, but the future one, next node after that will probably have graphene or some 2D material. I really don't know whether it's graphene or molybdenum disulfide or whatever. Yeah.
All right. Thank you very much.
Yeah.
So Prof Susi here. Can you hear me?
Yes, yes.
Yeah. Okay. Thank you, Prof, for a very like what Dr. Suhana mentioned. You started from the basics right until the current research. So thank you very much. So it's also a refresher course for us for the fundamentals. Thank you. So Prof, we can see the emergence of you know flexible electronics and electronics to be used for medical purposes like transient electronics and all, right?
Yes.
So where do you see CMOS transistors in that era, or where do you see it going, right?
Okay. Yes, correct. So actually this transistor of ours is a thin film transistor, right? The one that we showed, this is a thin film transistor. It can be done on flexible material and flexible substrates. And in fact, this group, Salahuddin and Suman Datta and all, they have actually showed they are moving. I think they are gradually moving towards the possibilities of using a ferroelectric FET as a memory device, 3-terminal ferroelectric FET as a memory device, and rather than as a CMOS node. And you can see that they are in one of their latest papers, they have actually put it as a thin film transistor. Ferroelectric memory, FRAM, is in a thin film transistor format, exactly like this, except that here they have got a ferroelectric material, which means they can get only 2 states of the device typically, whereas ours is a diffusive mechanism, so we can have multiple states of the device. So where it takes in terms of flexible electronics is, really we need, because of the IoT, we want to have computing locally on the device itself when it comes to sensing, because it just doesn't make sense to put so much data on the cloud. And I think that is being driven by edge computing, and we want flexible devices to have that capability to make decisions on the spot. And I think that's where the future will go, by means of these memory devices rather than looking at CMOS as such. Though right now CMOS is still very, very important, because you can't do a lot of things just alone with flexible devices. But ARM is working with plastic logic here, and they have come up with a processor for flexible, based on flexible materials. That is also the latest news last month.
Okay, thank you.
Yes.
Thank you, Prof. Thank you very much.
Yes, you're welcome.
Prof, we have one question from the chat.
Yes.
From Sharifah. Is it possible if you briefly elaborate on synaptic plasticity of, say, synaptic transistor devices that we need to look into should we want to build a neuromorphic device?
Where are we? You want me to explain this?
Dr. Sharifah?
Hello?
Yes. She answered yes.
You want me to go through this a little bit?
Because I know that there are many other plasticity variables, right? There's the SRDP, STDP. So should we look into every of these variables, or if we were to already say, say when we do the characterization, it satisfies this STDP, so we can say, okay, our neuromorphic device is working well?
I would definitely say you need to look at all types of plasticity. In fact, there's been so much research being done on how the brain, in all these brain projects, there are 3 brain projects going, one in Asia, one in America, and one in Europe. And they are revealing more and more the intricacies of brain, and they are beginning to doubt that this is one of the most simplest kind of crude thing which has been sort of for the last 50 years, people have assumed that this is the way it works, but there is a lot more that we don't understand. So I would agree with you that that we need to look into various types of plasticity. That's very, very important. Yes.
Thank you, Prof.
Yes. We should have devices which can mimic them. That is the goal for us as EDS society. But I don't think, we are there yet. We are very, very crude, very at a very basic level.
Thank you, Prof.
Okay.
Okay, it's already 5:10 here.
Okay.
Any more last question? There's none in the chat. Okay. Okay, so Prof. De Souza, on behalf of IEEE EDS, I would like to thank for your time to join our session. Thank you for your valuable time with us. It's a great honor to have you here. Thank you for your sharing such an impressive research work and fundamental work as well. We have an e-certificate. We are delighted to hand over virtually an e-certificate of appreciation to you. If we may project it here.
Oh, thank you. That's really kind of you. So okay. Do I have to press this take control?
No.
Okay. Thank you. Thank you. That's really kind of you, and thank you for your patience and for giving me this opportunity to speak.
Thank you so much, Prof, for everything. Before we end, can we quickly take a group photo?
Yes.
The attendees can kindly open your camera.
My camera is open.
The participants.
The participants.
Okay.
You can on the camera and
so Dr. Sana, you are going to take the picture.
You've got too much.
Hassan, can you help me to take?
Yeah?
Can you help me to take the...
Yeah, okay. Already. All right. Done. So the next page.
Thank you. Then we need to work around that. Welcome. You got done?
Just stick there.
No.
Leave me alone.
It's right.
So, all right.
Okay, thank you so much.
Okay, thank you so much. Thank you, everyone.
Prof. Thank you.
Thank you.
Yeah. We hope to see you in person someday.
Yeah.
Yes, I'd love to see you, and welcome to Sheffield. I know Sheffield already has a long link with Malaysia anyway, so it'll be wonderful to see, and you're more than welcome to our university, and I look forward to meeting you. Thank you for this opportunity. Thank you.
Yeah, on behalf of IEEE EDS Malaysia chapter, we would like to extend a special gratitude to you is very honored to receive our invitation for DL, and hope that we can have a more collaboration in the future between Prof. Souza, University of Sheffield with IEEE EDS Malaysia chapter.
I would welcome that. We very much welcome that. I'm very happy to collaborate and initiate new activities. I work in a number of areas, not just CMOS. I also work on flexible electronics, gallium nitride, and if there are students that want to work with me, I'm very happy to work with you and to support.
One more thing that we would like to extend an invitation for ICSE 2022, which will be conducted, we will have it in Langkawi, which is close to Penang.
Oh, nice. Very nice. Thank you.
So if you are available on that particular date, maybe perhaps you can visit Malaysia as well during that time.
I'd love to. I really would. Yes. Thank you. Thank you.
Right. Thank you very much. Thank you very much.
Thank you. Thank you.
Thank you, Prof.
Thank you,
Dr.
Susan.
Samen.
Thank you,
Thank you, Dr.
Susan.
Shohana. Bye-bye.
Thank you. Thank you.
Thank you, Prof. Susan.
Stay safe.
Stay safe, everyone. Thank you very much.
Thank you. Bye. Bye.
Bye-bye.
Okay, thanks all.